triple integrals in spherical coordinates. Spherical coordinates is another useful coordinate system in 3 dimensions, and it simplifies the evaluation of triple integral over regions bounded by sphere and cone, like this figure over here. A hot air balloon can be approximated with a cone and a hemisphere, both of which can be modeled easily in spherical coordinates. A triple integral of the solid gives the volume of this solid region. So you might wonder, when would you use spherical coordinates? Now, there are many regions that are easier to describe in spherical coordinate than in rectangular coordinates. Now, for those regions that require integration, a triple integral can be calculated in spherical coordinate system. For example, an astrophysicist can estimate the mass of a star by calculating the triple integral of the star's density function in spherical coordinates. Since the star is approximately spherical, the integral's bounds in spherical coordinates are constant. Another example, a geologist can calculate the average density within a particular region of Earth using triple integral in spherical coordinates. The region can be approximated using a portion of a spherical wedge. Now here's a tennis ball. A factory manager can determine the amount of rubber required to make the shape of a hollow sphere, such as a tennis ball, using integrals in spherical coordinates. Since the ball is the shape of a sphere, its outer surface and inner surface are easily represented in spherical coordinates. Oncology researchers study cancer, hoping to learn more and more about it, eventually curing it. Spherical coordinates are used in modeling tumors because spherical coordinates make surfaces that look vaguely spherical more straightforward to model them other coordinate systems. And we use the formula rho equal to 1 plus 1/5 sine of m theta times sine of n psi, where m and n are positive whole numbers, to get bumpy spheres that look like tumors. Programmers of Global Positioning System, GPS, can use spherical coordinates to express locations. Elevation is associated with rho, longitude is associated with theta, and latitude is associated with phi. Celestial coordinate systems are used to monitor positions of stars relative to a particular point. Astronomers use such a system expressed in spherical coordinates with rho as the distance from the center and theta and phi as the angles from two planes. The spherical coordinate of this point P here is rho, theta, and phi. Rho is the distance from the origin to this point P. Theta here is the same angle as in cylindrical coordinate. This is theta. Phi here is the angle between the positive z-axis and the line segment OP. Note that rho here has to be greater than or equal to 0, and phi, this angle, is going to be greater equal to 0 and less than or equal to pi. So from 0 to pi. The spherical coordinate system is especially useful in problems where there is symmetry about a point and the origin is placed at this point. For example, the sphere with center at the origin and radius c has this simple equation rho equal to c. And this is the reason for the name spherical coordinates. Now, what about this equation theta equal to c in spherical coordinate? Take a moment and think about it. For theta equal to c here, because rho has to be non-negative, we get a vertical half plane. Rho can only be greater than or equal to 0, so it cannot extend to the other side. What about this equation? Phi equal to c, a constant c. What does it represent? This equation, phi equal to c, remember, phi has to be greater than or equal to 0 and less than or equal to pi. So from 0 to pi, we have two situations. If c here is a number between 0 and power 2, we'll get this half cone over here with the z-axis here as its axis. And when c here is a number greater than power 2 and less than pi, we get a half cone like this. So this equation, phi equal to c, represents a half cone. Here we have a point P in rectangular coordinate. It has coordinate x, y, and z. In spherical coordinate, this point P has coordinates rho, theta, and phi. Rho, theta, and phi. Notice that x here is equal to this r here times cosine theta. Y is equal to r times sine of theta. Notice this r here is same as this distance here is also r. Therefore, r is equal to rho times sine of phi. So we can replace this r here by rho times sine of phi and get the equation that relate x with rho, phi, and theta, and also y with rho, phi, and theta. Looking at this right triangle over here, you see that z here is equal to rho times cosine of this angle, phi. Also, the distance formula shows that rho squared is equal to x squared plus y squared plus z squared. Because by Pythagorean theorem, rho squared is z squared plus r squared, but r squared is equal to x squared plus y squared. So rho squared is equal to x squared plus y squared plus z squared. We use this fourth equation to convert between spherical and rectangular coordinates. Let's try some examples. Example 1. This point 2, pi over 4, pi over 3 is given in spherical coordinates. Plug the point and phi is rectangular coordinates. So we plug the point here. Rho is 2. Theta here is pi over 4. And phi is pi over 3. And here's the point. Now we can find its rectangular coordinate x, y, z using all these formulas. Using these three formulas here, we get x is equal to rho sine phi times cosine theta. So we get 2 times sine of pi over 3 times cosine of pi over 4, and we got this result. Similarly, we get y equal to rho sine of phi times sine of theta, and we got square root of 3 over 2. And z is rho times cosine of phi, and the result here is 1. So this point in rectangular coordinate will be this point square root of 3 over 2, comma, square root of 3 over 2, comma, 1. Now, in the second example, we're going to convert rectangular coordinates into spherical coordinates. The first step to convert from rectangular to spherical is to figure out the rho first. From this equation, we are going to get rho is the square root of x squared plus y squared plus z squared. Plug in the x, y, z value, we get rho equal to 4. After you figure out the value for rho, we can make use of this equation to find out phi. From this equation, we get cosine of phi is z over rho, and the result here is negative 1/2. Remember that phi is greater than or equal to 0 and less than or equal to pi, so phi here has to be equal to 2 pi over 3. The last step here is to figure out theta. Using either this or this equation. Let's use this first equation. So cosine theta is equal to x over rho times sine of phi. Since x equal to 0, this result here is equal to 0. So theta will be equal to pi over 2. Notice that theta doesn't equal to 3 pi over 2 because we have a positive y coordinate. Therefore, the spherical coordinate of this given point in rectangular coordinate is 4, pi over 2, 2 pi over 3. In spherical coordinates, the counterpart of a rectangular box is a spherical wedge. This spherical wedge can be described by this set here, where rho is between A and B, theta between alpha and beta, and phi between C and D, where A here has to be a non-negative number, and the difference beta minus alpha is less than or equal to 2 pi. The difference D minus C is less than or equal to pi. So they're not more than pi apart, and here they're not more than 2 pi apart. We can divide this spherical wedge into smaller spherical wedges, like subwedges, by means of equally spaced sphere rho equal to rho I, and half plane theta equal to theta j, and half cone phi equal to phi k. And you look at this figure here, think about this is one of the spherical subwedges. The volume of this spherical subwedge can be approximately equal to this. Think about this is the height times the length times the thickness. And here, this is delta rho. Here is rho I times delta phi. And here is rho I times sine of phi k, and then times delta of theta. So you see, how do you get this part here? This part over here is the same as this one over here. Remember, we think about that like the part of the big circle with radius from here to here. Then we use the radius times delta data. Now that radius over here is this Ri. And looking at this green over here, this radius, that's the same as rho I times sine of phi k. Sine of phi k is right here, and this is rho. So this is the opposite side of this angle. So it will be this rho I times sine of this angle. So give you the green one. And then using that to multiply with delta data, that will give you this arc length over here. So this times this times this give you an approximation to the volume of this spherical wedge, which is equal to this. Using the mean value theorem, we're able to show that the volume for that wedge is actually equal to this, where this point is some point inside the wedge. And we're going to let this point here be the rectangular coordinate of this point. This is in spherical coordinate. We let this to be the rectangular coordinate of this point. Then the triple integral of a function over this solid is equal to the limit of this Riemann sum, this triple Riemann sum. So it's a function value at this point, and here is the value for that wedge. And letting L, M, and N go to infinity, this triple Riemann sum is going to approach to this triple integral of this function over the solid. But this sum over here is a Riemann sum for this function of rho, theta, and phi. Remember, when L, M, and N go to infinity, this is going to be replaced by rho, replaced by phi, replaced by theta. And similarly, all of this replaced by rho, replaced by phi, replaced by theta. So that sum here is a Riemann sum for this function f of rho times sine of phi times cosine of theta, rho times sine of phi times sine of theta, rho times cosine of phi, and here will be rho squared, here will be sine of phi. So therefore, we come up this formula for triple integration in spherical coordinates. Now, this formula here says that we can convert a triple integral from rectangular coordinate to spherical coordinate by writing the x here by this expression, y by this expression, and z by this expression. And the dv over here is replaced by rho squared sine phi d rho d theta d phi. This is called the volume element in spherical coordinate. dv is equal to this, as we see from this picture. We can extend this formula to include more general spherical region, such as the rho here is not necessarily be bounded above and below by a and b. It could be bounded below and above by two functions. And if rho here is bounded by g1 and g2, then instead of rho go from a to b, we can replace a here by g1 and b here by g2. When do we use spherical coordinates in triple integrals? We use them when the boundary of the region of integration are made up of surfaces such as cones, spheres, hemispheres or regions with spherical symmetry. Now, the next example, we would like to evaluate this triple integral where B is the unit ball over here. Notice that the boundary of this ball here is a sphere, so we're going to use spherical coordinate. Rho over here go from 0 to 1. Theta go from 0 to 2 pi. And phi go from 0 to pi. Notice that the function that we integrate with involve x squared plus y squared plus z squared. So we should also use spherical coordinate because x squared plus y squared plus z squared is equal to rho squared. So rho squared to the 3/2 power, we multiply this two number, so we get rho to the third power. So the function that we integrate with will be e to the rho to the third power. Remember this value element is replaced by rho squared sin phi d rho d theta d phi. Now because this function that we integrate can be broken up into a function of rho times a function of phi, and also all the limits of integrations are constants. Then we can separate this as the product of these three integrals. The first integral here is the integral of this function that involve is a function of phi, and then d phi. Phi go from 0 to pi. And here is a function of theta, and you don't see a theta here. So think about the function here is the constant 1. So theta go from 0 to 2 pi. Finally, times the integral of this function of rho go from 0 to 1. So we can break this triple integral here as the product of the integral, the first one with respect to phi, second one with respect to theta, and the last one with respect to rho. Taking antiderivative here and evaluating, we got this result. Example 4. Use spherical coordinate to find the volume of this solid that lie above this cone and below this sphere. Now, this equation of the sphere, we can rewrite this x squared plus y squared plus z squared as rho squared. Notice that x squared plus y squared plus z squared is equal to rho squared, and z is equal to rho cosine of phi. Rho here does not equal to 0, so we can divide both sides by rho. We get rho equal to cosine of phi. And as you can see here, from here to here is 1. That's the diameter for this circle. It's 1. Phi here is this angle formed by the positive z-axis to this ray over here. That's phi. This is a y angle. Rho is equal to 1 times cosine of phi. Now, if we take this equation and move the z to this side, so subtract z on both sides, we can actually complete the square. So we can complete the square here. Take the coefficient for z here and divide by 2, and then square and put it here. This 3 term here is going to become this perfect square of z minus 1/2 perfect square. 1/4 is the square of 1/2. So this gives us the center for the sphere is 0, 0, 1/2, which is this point over here. Now this equation over here actually makes sense because for that circle, this big circle here, the diameter is 1, and this angle here is phi. Rho here, because this is a y triangle, rho here is equal to 1 times cosine of this phi. We call that volume of a solid is equal to the triple integral of the function 1 over the solid. So replacing this volume element dv by rho square sine phi d rho d theta d phi. Rho go from 0 to, see this surface here is rho equal to cosine of phi. So rho go from 0 to cosine of phi. So rho go from 0 to cosine of phi. 0 to cosine of phi. Now d theta. Theta is this angle. Theta go from 0 to 2 pi. So 0 to 2 pi. Now what about phi? Phi, the smallest angle here is phi equal to 0. And the biggest phi here is pi over 4. So how do we know that this angle is pi over 4? We got the equation for the cone is z equal to square root of x squared plus y squared. Remember z is equal to rho times cosine of phi. So we replace z by rho times cosine of phi. Square root of x squared plus y squared. Remember x is equal to rho times sine phi cosine theta. So we square that one, we get x squared is rho squared sine squared phi cosine squared theta. And we replace y squared by rho squared sine squared phi sine squared theta. Now we can take out this common factor, rho squared sine squared phi, and we have this cosine squared theta plus sine squared theta inside the parenthesis, which is equal to 1. So square root of rho squared sine squared phi is equal to rho sine phi. These two are equal. Divide both sides by rho because rho is not equal to 0. We get cosine of phi equal to sine of phi, which means tangent of phi equal to 1. And phi is between 0 and pi, so phi is equal to pi over 4. Another way to see this angle phi here is pi over 4 is by solving these two equations together, solve for z. So we can replace this x squared plus y squared here by z squared because z is the square root of x squared plus y squared. So this is z squared. Adding z squared equal to z. Now we get this quadratic equation. We take out the common factor z. Z times 2z minus 1 equals 0. Z equal to 0 or equal to 1/2. When z equal to 1/2, the horizontal plane z equal to 1/2 is going to cut this sphere in the middle. So this angle here has to be equal to pi over 4. So therefore, we can describe this solid E in spherical coordinate. So this figure over here, we can see how this solid is swiped out by first letting rho go from 0 to cosine of phi. Remember, rho equal cosine phi is the equation for this surface, the upper sphere over here. And at this time, we keep the phi and theta to be constant. And now we're going to let phi here vary from 0. So over here, phi is equal to 0 for this one. And then it's going to go to power 4. So it opens up like this, like a fan. So open up like that. So this ray over here, so it's going to sweep out this blue region over here. Now we're going to, at this time, we keep the data to be constant. Now, finally, we let data, we go from 0 to 2 pi. So we rotate this blue region and rotate that 2 pi. We get the whole solid. So rho go from 0 to cosine of phi. Phi go from 0 to power 4. And theta go from 0 and rotate one rotation. So it go from 0 to 2 pi. So pay attention here to evaluate this integral because this upper limit here is not a constant. We cannot break this triple integral here as the product of 3 single integral because in order to do that, the upper and lower limit here has to be all constants. So because of this, we cannot do that. Then we can evaluate this triple integral by first evaluate the innermost integral and then work from inside to outside. Another way to evaluate this triple integral, notice that this function that we integrate contains no data, it's independent of data, and data go from a constant to a constant. So we can break this triple integral as the product of this integral with respect to data times this double integral, first with respect to rho and then with respect to phi. Notice that the upper limit here for rho is not a constant, it is a function of phi. We cannot break this as the product of two single integrals. The integral of 1 when data go from 0 to 2 pi is equal to 2 pi. And for this double integral, we have to evaluate the inner integral first. The inner integral with respect to rho, we regard the sin phi here as a constant multiple. So sin phi here, antideuty of rho square is rho q over 3. Rho go from 0 to cosine of phi. Substituting rho equal to cosine of phi and rho equal 0 in, we got this result. Now we need to integrate this with respect to phi. We can use u sub. We can let u equal to cosine of phi. So sin phi d phi is negative du. So antideuty of this with respect to phi is negative cosine to the 4 power phi divided by 4 and then divided by 3, so which is the same as divided by 12. Now substituting phi to be power 4 and phi to be 0 in here and do the calculation, we got the value for this solid here is pi over 8. Notice that for the whole sphere here, because the radius here is, the radius for the sphere here is 1/2, the value for the sphere is going to be 4 over 3 times pi r cubed. So it's 4 over 3 times pi times 1/2 cubed. So we got 4 pi over 3 times 1/8. So the total value for the sphere will be 4 over 3 times the value of this cone together with this half sphere. In other words, the volume of the solid we found is 3/4 of the volume of the sphere.